This is Content Objective 2 for Section 2.2, the limit of a function, and with this objective we will be using limit notation to represent vertical asymptotes. So by the time we're done with this section, or this objective, you should be able to explain the connection between the limit representation of a vertical asymptote and what is occurring graphically to the function's x and y coordinates. So the first thing we want to do is we want to connect to old knowledge and think about how we recognize vertical asymptotes when we see them on a graph. And we have an example here that kind of shows that there's a vertical asymptote here at 0, and what we see graphically is that the y coordinates are getting super high no matter which side we approach from. So we see these vertical asymptotes when we see really sharp, quick upticks in y values, either heading up toward positive infinity. We could also see them heading down toward negative infinity. So for this example, we want to consider the curve f of x equals 1 over x squared, and we want to be looking at what happens to the y coordinates as x gets closer and closer to 0. We have it two ways. You can either look on the graph or you can look in the chart. If I hop to the left of, to the right of 0, and I travel along the curve as I'm trying to get that x coordinate closer and closer to 0, we see that the y values are getting bigger and bigger and bigger, and we never actually get to 0 because we just keep shooting up higher and higher off the graph. Same thing if I hop to the left of 0 and travel along the curve. We see that those y coordinates are getting larger and larger and larger. On our table of data, we can see that if we start to the left or right, say at 1, and we get increasingly closer and closer to 0, the outputs of the function are getting larger and larger and larger. So this is a numerical representation of a vertical asymptote. We also have a graphical representation of a vertical asymptote. Well, we also are going to need an analytical or an algebraic representation of an asymptote, and this is where the calculus comes into play. The algebraic notation that we use to represent vertical asymptotes involves limits. So in this case we have a limit of f of x as x approaches a from both sides equals infinity to represent that the values of f can be made arbitrarily large by taking x sufficiently close to a. So in layman terms, what that means for us is that if we hop on the curve to the left and right of a, and then we move closer and closer to an x value of a, those y values are both heading up to positive infinity. So both thumbs will travel up. By contrast, we can write the limit as x approaches a from both sides of f of x equals negative infinity. When that is written, it means that the y values can get arbitrarily small as x gets closer and closer to a. So in layman's terms, if we hop on the curve to the left and right of a, then both thumbs are going to travel down as we get closer and closer to a from both sides. We can use similar notations to represent one-sided limits. So what I'd like to do here for a second is draw little pictures that go with each of these so that you can kind of see how it works graphically. This first one says that as we're approaching a from the right hand side, the y coordinates are getting really big in the positive direction. So that means my graph would be heading up to positive infinity from the right. By contrast, over here, as we're approaching a from the left side, the y coordinates need to be getting bigger. This one says as x approaches a from the right, this time the y coordinates are going to head down. And this one says as we approach a from the left, again those y coordinates are going to be heading down. So these are analytical representations of this type of behavior. So knowing what all those behaviors are should enable you to explain the connection between the limit representation of a vertical asymptote and what's occurring graphically to the function's x and y coordinates. So again, we have some vocabulary to help us deal with vertical asymptotes. It turns out that the line x equals a will be a vertical asymptote on the curve of y equals f of x if at least one of the following statements is true. We can either have the limit as x approaches a of f of x equals infinity, or that limit will equal negative infinity, or any of these four one-sided limits involving infinity or negative infinity can be true. So if we get any of the incarnations where y coordinates are becoming unbounded as we approach an x value of a, then x equals a will be considered a vertical asymptote. So this enables us to go back and forth between this notation and the equations of vertical asymptotes. For example, if we look at a, we can see that as we're approaching 3, something funky is happening to the y coordinates. So we can say that x equals 3 is a vertical asymptote. Here, as x approaches negative 5, the y coordinates are becoming unbounded. So that means x equals negative 5 is a vertical asymptote. Here, as x approaches 4, again, the y coordinates are becoming unbounded. So x equals 4 is a vertical asymptote. And as x approaches negative 2, the y coordinates are getting very large. So x equals negative 2 is a vertical asymptote. Now if we wanted to represent all of these graphically, here we'd have a vertical asymptote at 3, and we're approaching it from the right and heading down. Here we have a vertical asymptote at negative 5. And as we're approaching from the left, we're heading up. Here we have a vertical asymptote at 4. And as we approach from both sides, we're heading down. And the last one, we've got a vertical asymptote at negative 2. And we again are approaching from both sides and heading up. Little sloppy there, but you get the gist. So now the goal is, how are we going to recognize vertical asymptotes when we see them analytically? Well, this is one of the ways if we already know the infinities that are involved. But let's say I'm given a function f and I want to know where the vertical asymptotes are. Well, this is going to require that we remember things we did in Algebra 2 and in pre-calculus. So we got to think about when vertical asymptotes happened in those classes before we knew anything about limits. What I hope you will recall is that vertical asymptotes occurred in your Algebra 2 classes and in your pre-calculus classes whenever you ran into problems in the domain. You never had vertical asymptotes outside of those problems. So that means we need to remember what caused problems in the domain for us. So there are three main categories of problems. The first is if you try to divide by 0. The second is when you've got negatives under an even root. The third is when you try to put non-positives inside logs. Now some of these generate vertical asymptotes graphically and others don't. So let's go through those just a little bit one at a time. If you try to divide by 0, they will be manifested graphically in one of three ways. You will either see a vertical asymptote, or you will see a hole, or you will see an oscillation. And we'll talk more about when you see which of these later on, but for right now I just want to give you a quick overview. So, for example, on this one, if I try to plug in a -2 for x, that generates a 0 on the denominator that gets manifested graphically as a vertical asymptote. Over here, if I try to divide by 0 by plugging in a +2, I end up with a hole, whereas if I plug in a -2, I end up with a vertical asymptote. So here we had two problems in the domain, both of which were division by 0, and only one of them generated the asymptote. This third type, which is trig, this is where you'll see those oscillations, is if you're trying to divide by 0 inside a trig function. When that happens, you start to oscillate very quickly, frenetically. I mean, it just starts going crazy and crazy the closer you get to x. If you were to zoom in graphically on your calculator on this function's graph, you would see it just wigging out when you get closer and closer to that 0. So that's an example of an oscillation manifestation of a division by 0. We also have negatives under even roots. Now, with root functions, when you try to put numbers in that are not in the domain, you don't see any graph at all. So you don't get a vertical asymptote with this type of a problem. Instead, you just get an abrupt end to the graph and then nothing else to the left. So these negatives under even roots, even though they're problems in the domain, they are not going to generate vertical asymptotes for you. So if your job is to look for vertical asymptotes, you're not going to worry about the roots. You're going to look for division by 0, and you're going to look for logs. Because what happens with the logs, since they're undefined, if you put a non-positive inside, it means that the closer and closer you get to a 0 on the inside of that log, the more of a problem you're going to have, and you'll see that problem manifested as an asymptote. So in this particular case, when x is -3, when I plug a -3 into that, I get an undefined output, and if I plug numbers that are really close to -3, but on the right of -3, I get outputs that are more and more and more negative. So we get a vertical asymptote when we try to put zeros inside logs, and we get vertical asymptotes sometimes when we try to divide by 0. So let's look at a few examples of where we're trying to come up with the vertical asymptotes for the functions. And then we're going to support that by writing the limit statement that means there's a vertical asymptote there. So if we look at part A here, we have f of x equals x over x squared minus x minus 2. Well, in order to identify the problems in the domain, I can see that I have no logs and I have no pieces. So the only place where I've got candidates for a vertical asymptote are going to be if I try to divide by 0. So to identify those, I'm going to factor the bottom. I've got an x minus a 2 and an x plus a 1. So I can see that there are going to be issues at x equals -1 and at x equals +2. If I graph this curve, x equals -1 is going to be a vertical asymptote, and x equals +2 will also be a vertical asymptote. Notice I did not give you a hole yet because that's a nuance that we're not going to work on for a little bit. And now I want to just try and test some points. I know that if I plug in x equals 0, I'm going to get a 0 on the top. So I can plug in that point right now. I've got a nice intercept. Now if I get closer and closer to 2 from the left-hand side, to 2 from the left-hand side, that means I'm plugging in a number. I know I've got an asymptote, so I'm either going to be heading up to positive infinity or down to negative infinity. So what's important to remember about this particular term is whether it is positive or negative. If I plug in something a little bit larger than 2, then the top's going to be close to +2, so it'll be positive. This factor will be a little bit bigger than 0 because I took something larger than 2 and subtracted a 2, so this piece will be positive. And then something close to 2 plus 1 is also positive. So I have 3 positives in this expression, so the overall result will be positive, which means I'm heading up toward that asymptote. If I look on the left-hand side of 2, say at 1.999, this top will still be positive. This will also be positive, but now this expression or this factor will be negative because a 1.999 minus a 2 is going to give me a negative value. So that means a positive divided by a negative and a positive, the overall result will be negative. So I will be traveling down on that asymptote. If I look at 1 now, or excuse me, at -1, I can go a little bit bigger. So let's say I'm at -0.999. The top will be negative, this will be negative, and a -0.999 plus a 1 is a positive value. So I have 2 negatives and a positive will end up giving me a positive. So I'm going to be up as I approach that asymptote from the right. If I head toward -1 from the left, say at -1.001, this will be negative, this one will be negative, and this one will also be negative. So I'll have 3 negatives, and I'll end up getting a picture that looks something like this. So here we've got a graph that verifies that we have vertical asymptotes at x equals -1 and x equals 2. And there are several different vertical asymptote limit justifications that we could write. I really only need one per vertical asymptote. So I could say the limit as I approached 2 from the right-hand side on f was positive infinity, because as I was coming toward 2 from the right, I headed up. And I could do the limit as x approaches -1 from the left would be negative infinity. So here's my -1. I'm hopping on the curve to the left and heading down. All right, so let's look at part B. Part B says f of x equals tangent of x. And I told you earlier that every vertical asymptote has to come from problems in the domain or joints on a piecewise function. There are no joints here, so that means I'm looking at problems in the domain. And the only problems in the domain that generate issues that are manifested as vertical asymptotes are division by 0 or zeros in logs. There are no logs here, so that means we're looking only at division by 0. But I don't see any division here. So this is actually a division problem that has been hidden from you. You have to remember from your trig that you did last year that tangent is the same as sine over cosine. So that means you're going to get asymptotes every time cosine of x is 0. So if you think graphically, if you remember what your tangent looks like, you can remember that you've got asymptotes at pi over 2 and at negative pi over 2. And then you repeat because you have a periodic function. So every time that cosine was 0, we end up with an asymptote on the tangent graph. So that's going to be when x equals pi over 2 plus a period of the tangent curve. So what is the period of the tangent curve? It is 1 pi across from each other. So we can do a pi times an integer. So at every single one of these places we are going to have a vertical asymptote. We can write the limit statements for these by saying the limit as x approaches any of these. We should probably say that n is an integer of that function is going to be, well, we got to decide whether we want to come at it from the right or from the left. So if we come at it from the right-hand side, we're heading down every single time. So there's a limit statement that justifies for us that vertical asymptotes that are occurring at each of these locations. Okay, the next one, we have f of x equals the log natural now of x squared minus 9. So again, vertical asymptotes only occur when I've got issues with the domain, where those issues are division by 0 or zeros inside logs. Since this one has a log, we're looking at when the inside of this thing equals 0. If I solve for x, I'll get plus or minus 3. So graphically, I'm going to have vertical asymptotes at plus or minus 3. And remember that log naturals are not defined, or any log is not defined for negative inputs. So that means we are going to have a graph that looks like a log natural on the left and on the right. So I have two vertical asymptotes where x is 3 and x is -3, and I can justify using limit statements and approach those 3's from the correct direction. Remember, you can only approach from directions that you actually have curve. So this asymptote of 3, I've only got curve on the right, so I'm going to have to approach it from the right-hand side. And notice that the y coordinates are heading down as I get closer and closer to x equals 3. For the -3, I can only approach from the left because that's the only place I have curve. So if I'm approaching from the left, notice again my curve is heading down, so I have negative infinity. Here we have an example that involves asymptotes at a joint. So what we need to look at here is, first, can we draw the picture, kind of see what's going on? We've got the reciprocal curve when x is less than 0, and then we're on a line when x is greater than or equal to 0. So if I have a value of x that's smaller than 0, and I divide 1 by that number, I'm going to get a negative number that's getting increasingly larger and larger as we approach, whose magnitude, I should say, is getting increasingly larger as we approach 0 from the left-hand side. And as we get out further toward negative infinity, the output of this gets closer and closer to 0. So our picture looks something like this on the left-hand side. And on the right-hand side, we're on the equation of a line whose y-intercept is 1 and whose slope is positive 1. Notice that I have this equal underneath here, so that means I get to fill the circle. Now, our goal is to identify the vertical asymptotes. Remember, asymptotes occur either at joints or when we have problems in the domain, such as division by 0 or zeros in logs. So I can see a division by 0 happening here when x approaches 0, and I also see that 0 is the joint between the two branches of the curve. So graphically, we can see that that x equals 0 is a vertical asymptote, and the limit statement that we have to use to justify it is that as I approach that 0 from the left-hand side, that's when it's blowing up on me, then that limit is negative infinity. So what I'd like you to do now is to list the steps that we have done to identify the equations of functions' vertical asymptotes on these 4 examples.